Hello again. This is potentially the last in the series of gravity wave related presentations. If something new and different comes up, Anton Petrov says something new and different. I might do another one in the future, but at the moment, there's nothing in the pipeline. But tonight, we're going to talk about the electromagnetic spectrum or EM spectrum versus the gravity wave spectrum or GW. And under what circumstances are they considered discrete or continuous? And I'll explain the difference between the two. There is a distinction between what something is and what it's proclaimed to be absent full qualification. You can never say nothing is never something, but you can broadly say it's generally this, but theoretically, there should never be a circumstance where it's not that. That's why I describe it as what it is versus what it's proclaimed, because if it's proclaimed in general agreement, and you didn't survey every possible potential and didn't find any, then the proclamation sticks. If you want photons to be teased out of atoms, electrons, then you excite them by applying energy. You're not actually stripping the electron away. You're not ionizing it. You're just exciting it. So it will move up an orbital, spit out a photon, and then go back down an orbital. And when you do that, it can only go up a certain amount based upon the energy that's applied, and it has to be an integral value. So you can't get like halfway there and you get like half as energetic a photon or more, and then the leftover excess would be something else. It's precise integer or integral. It's not actually integers because they're, if you look at the electron volt levels, there's fractions, but Heisenberg uncertainty comes in, but it's generally specific frequency bands that you can get, specific wavelength bands based upon the orbitals. And yet they'll talk about ionization emissions as being, not ionization, but excitation emissions as being continuous and not discrete. But at the individual level, they are discrete, but they're wide band discrete. They're not like single line. But they proclaim the electromagnetic spectrum as being continuous, meaning no gaps. And yet, if you look at the table that the U.S. National Institute of Science and Technology provides for electron volt excitation levels, you'll see that there's specific center line numbers and there's gaps between them. But that's not the only way you can tease photons out of atoms or even free roaming electrons. So when photons are produced, that's referred to as emissions. When photons are absorbed, that's referred to as absorption. If you look at a spectrum from like a star, that spectrum will have black lines in it. And the black lines are where the photons are absorbed. So the spectrum literally has low photon flux or low count photons at those wavelengths. That's those gaps. It tried to produce them. It's just they got absorbed. And that's why you have gaps. So if you were to just look at a spectrum, you wouldn't think that photon emissions were continuous because they have these gaps. But there are other ways that you can essentially make those occur. So I mentioned in a presentation maybe better part of a year ago, this thing called Bremsstrahlung radiation. That's where you essentially accelerate an electron, and then in a magnetic field, you bring it to a quick stop, and it's got to conserve the energy. So it's got to ditch that excess energy that brought it to a stop, and that comes out as a photon. And that particular photon is related to the magnetic field strength and the energy imparted in that moving electron. So we know that the electron's energy can be discrete, but the electromagnetic field that you're presenting there can be pretty much far more continuous. And therefore, when it stops, the photon that comes out can be a photon that would fill the gap that would normally be between the emission levels in an atom. So there's a way of filling the gaps. There's also black body radiation, which is, it's called black body, but it's essentially all colors, wideband radiation. So that's a way to fill it. So because there's gaps in the integral emissions, if we just stop there, we could say it's not continuous. But we've got these other ways of spitting out photons, Bremsstrahlung and black body, that will produce photons at all those different ranges. and therefore it's continuous. And there are other ways of doing it too. There's broadening, both natural and pressure and thermal, due to molecular interactions, molecules interacting with one another. There's the ever popular Doppler shift, how how fast things are moving away. That doesn't have any discrete values on it. So the amount of red or blue shifting can produce new wavelengths of red or blue light. They would also fill in those gaps. And then the actual shifting of space itself, gravity wave space time dilation, as the gravity wave ripples through, it expands and contracts things. And that's short-lived. As the ripple moves through, it can actually shift the wavelength of the photons. And that's why we use interferometers to find them. But as soon as the gravity wave rolls through, it goes back to whatever it was after some dampening period. So I like to think of it as, okay, everybody agree we've got all these ways that photons can be produced. And even though the electrons associated with atoms will produce discrete values, we've got all these things capable of filling it in. So it's possible to have a photon at any wavelength, although the amount of them you can generate may be a lot less. You know, if you're exciting electrons in an atom, you may have very bright emission bands, but if you're only getting them from Bremsstrahlung radiation, it may only fill in like a small number of gaps near the X-ray portion of the spectrum. So it's kind of a, okay, let's all agree that electromagnetic spectrum is continuous by proclamation. And there's no doubt in that. Yeah, you can't controllably get everything you want. Like when you look at white light coming from a purportedly white LED, if you actually look at the spectra, there's absorption lines in it. It's mostly everything, but there are gaps. I think of it as groupthink. It's a proclamation. Everybody face the same direction and believe it. It is continuous. Given all possible scenarios, it's continuous. But remember me saying that under certain absorptions, there are very few photons at certain frequencies, and they actually refer to these as water holes. And it's not to do with the Earth's atmosphere, moisture absorbs the photons coming in, and therefore certain radio bands can't receive. It's more like, well, there's very few sources producing those particular frequencies, and therefore it's a somewhat quiet portion of the electromagnetic spectrum in certain radio frequencies. And the band is 1420 to 1662 megahertz, or 18 to 21 centimeter if you're into wavelengths. And the hydrogen line, the primary hydrogen line, is at the bottom of that. That's the ever popular 1420.40575, or 21 centimeter. But there's also another water hole, because we don't have any technology to listen to it, to receive it, and that's below 3 hertz, below the extremely low frequency. There may be things down there, but since we have no radio that can pick it up, we don't know. But there's no reason why there shouldn't be stuff down there if it's truly continuous. So that was the EM spectrum. Gravitational waves, or GW, it appears to have its own spectrum. It's not the same per se. They are two different spectra, two different mediums, two different sources, but they both seem to have the same kinds of characteristics of wavelengths and frequencies and phases and such. But from what we can tell, the GW spectrum should also be continuous because it's mass associated, as far as we can tell right now. Mass does not have a specific, mass can be this, but it can't be that, but it can be this. So there's no known gaps. Mass can be, unless you measure it down to the individual atom of a planet or a moon, they can be pretty much any size. Now, when they get to a certain small size, it's kind of more difficult for it to stay, for it to get hydrostatic equilibrium and hold together. It's just a loose rubble pile, but it still has mass. So if it's moving around in space and it can affect something that's even smaller, that'll produce a gravity wave, but we just don't have the technology for detecting it. Like I've mentioned previously, there are very low-level gravity waves, very long wavelength, low level, like mass dampers in skyscrapers, electromagnetic catapults on modern aircraft carriers. These all produce a very high mass that comes to an abrupt stop, and that would create a gravity wave. So we found that atmospheric fronts, the fluid of the atmosphere as the Earth rotates, actually produces a gravity wave effect in the Earth's atmosphere. Ocean waves, when you're moving that much mass and it comes up to the shoreline and it breaks on the shoreline, that amount of mass moving and then suddenly stopping can induce a gravity wave. These are gravity waves that we recognize. We use satellites to observe them, but we can't generate them. They just are. But we don't have any medium level gravity wave examples. So we've got the small stuff and we've got the very big stuff like things that collide out in space, but we don't have any examples of this big swath in the middle of down at the low end where we can't pick them up, and then the very high end where we can obviously pick them up with pulsar timing arrays and stuff like that and interferometers. But there's a huge gap between those two ends that we don't have any good examples of them. Do they exist? Well, theoretically, since mass can be granular down to the individual particle, individual atom, theoretically it's continuous. We're just missing all the examples that fit in there. And the gaps are non-trivial. The distance between the middle and the high levels is a lot of wavelength, but it's impractical to special create instruments to see if there's anything in those gaps. And remember, a gravity wave is probably passing through you right now, and there's no harm to you. You don't feel it. It's kind of like neutrinos and just go through and never saw it, never heard it. So if there are samples in these gaps, we don't have any technology for detecting it at the moment. We know that the EM spectrum has both emission and absorption. This is how we get the lines, but we're not aware of any ability to absorb gravity waves, to basically put a stop to a gravity wave once it's initiated, and they roll through space-time, matter, stars, everything. We're getting gravity waves from other galaxies. So pretty much nothing stops them. So there should not be an absorption line in the gravity wave spectrum. But until we find one, we won't have any proof of it. And when a gravity wave rolls through, it seems to be doing so in a lossless manner. And we know this because the LIGO detectors here in the US, we have one in the East and we have one out in the West. And the one in the East can sense a gravity wave. And then shortly thereafter, the one in the West can sense the same gravity wave. So it didn't lose a lot of energy, by traversing a quarter of the way through the Earth. But we can still say it's continuous until we have proof otherwise. So much like the EM spectrum has quiet bands, the gravity wave spectrum should also have quiet bands or water holes. These would be that gap area where we're talking about the minimums and maximums of masses of things. So the mass gap between the largest planet, something that's 13 Jupiter masses, about 4,000 Earth masses, that's kind of like the largest thing that we call a planet. And then the smallest thing that we call a star, which I don't have the mass equivalents here, but let me just say that the largest planet that we've theoretically and observed, observation, detected, and confirmed, that largest planet is bigger than the smallest star that we've detected. So there's theoretically a gap between the biggest planet and the smallest star, but we don't find a lot of those smallest stars. So the gap from biggest planet to healthy sized but small star, that area should be a gravity wave gap. But until we actually confirm its existence, we don't really know. But that should be
we differentiate the stars is by deuterium fusion. So even though they are like brown dwarfs, very cold stars that barely, if they have some fusion, sometimes even lithium in the beginning of their lives, and then later just deuterium fusion, they still consider a star. And the extremely large planets only have the heat from Kelvin Helmholtz cooling. So as they are hot in the beginning, and they contract and let it go some the heat, and it gets smaller and smaller. And so the planets tend to get smaller as they age because of the Kelvin Helmholtz cooling. And then the stars, as long as they have some deuterium to burn, they can still produce their own heat. And so that's kind of the difference. And sometimes, because the stars are more massive than the planets, they are smaller because they can kind of squeeze stuff together than the planets. It's like, it's weird. If you look at the volume, some of those large planets are very big, and they're way much bigger than stars because those stars are more massive and they are contracting the matter.
Yeah, this is why I say there's probably a mass gap between the largest of planets and the higher population of smallest of stars. You have different categories of stars based upon their temperature. So you could have a class of stars that would be the popular low end, but there would still be stars that were smaller than that. And those stars would be smaller than the biggest of planets, but there would be fewer of those than the main sequence stars. So if we wanted to listen to a water hole in the gravitational wave spectrum, where would that be? Well, in the electromagnetic spectrum around the hydrogen line, we monitor that in radio astronomy. But at the moment, we don't monitor the water hole for gravity waves because we would have to develop specific instruments that would work in that band, that wavelength, that frequency. And we don't have any instruments that do that. The pulsar timing arrays are looking for very much longer wavelengths, and the laser interferometers are looking at very much shorter wavelengths. This would be in the middle. So how do you go convince somebody to give you, many millions to maybe $1 billion to go create some new technology observatory that would detect where you don't think there's going to be gravity waves, the quiet spot. So it'll be interesting to see if someday, when they realize there's a lot broader gravity wave spectrum than we initially thought, to maybe want to listen to the gap.
I have a question.
Yes.
So far, we can only detect collisions, right?
No.
What else can we detect?
We can detect the gravity wave background.
Okay, but this is the microwave ground. It's from older collisions from long ago that they are permeating everywhere.
Right, but we don't know. We're just assuming they were collisions. We don't know because it's a what do they call it? An anesotropic background. We don't know.
Anisotropic.
We don't know the source of every single thing that we're observing. It's just uniform. But yeah, back from the early formation of the universe, we can detect a gravity wave background, and that we don't know the sources from. But yes, everything that we've detected with the laser interferometers have all been essentially high-speed orbits or collisions. And the orbits, because they're spiraling in, are short-lived, and the collisions are obviously short-lived. So we would be looking for much longer-lived, near continuous. If I've got good-sized star orbiting another good-sized star, but they're not going to collide, they're in stable orbit, that's going to produce a gravity wave because you've got two enormous masses orbiting each other. There's going to be
So that one we call it frame dragging, if I'm not mistaken.
Right, but we've detected frame dragging optically, but we haven't detected it as a gravity wave yet because we don't have the observatory with the instruments to do that, because we're only looking at gravity waves that are like light year long, plus that's the pulsar timing array, and then the laser interferometers, which are looking for the other ones. We need to create new technology instruments, even if it's indirect, like we do with Cherenkov radiation. Even if we have to look at this to see that, we need to look in the middle for those other gravity waves. So we're just assuming that the gravity wave spectrum is continuous, because if mass is the source of the gravity waves, mass is continuous. It's impractical to fully verify the entirety of a spectrum as continuous. You just, here's where the bulk of it comes from. Here's the potential for the fillers that make it continuous. Therefore, it's continuous. And we've done that for the electromagnetic spectrum. We have yet to conclude that for the gravity wave spectrum, but there's nothing stopping it from doing so. We need to look at spending the money to create a gravity wave band receiver that would listen to the water hole, much like we spend money on hydrogen line listening in the EM band. Maybe there's somebody out there already sending, and if they are, we'd have to recognize that it's modulated and then see if we can listen. But to listen, we would have to see that it's there, demodulate it, decode it, and then translate it. And we're a long way off from that, but let's look for the signal first. And then lots of links.
That's a hard word to pronounce.
Bremsstrahlung?
Bremsstrahlung.
Manuela does it best. Okay. I knew it was going to be a short one. That's why I didn't have a problem with us taking a lot of time up front to discuss other topics like smart scopes.
Right.
Comments, questions?
Yeah. If a gravity wave is propagating towards us, don't we ride along with it when it envelops us? How can we detect it?
There is that science fiction phenomenon of, well, we're going to surf the wave like a surfer would surf the wave. Apparently, that's not the case as far as we can tell. But then space-time does not have registered coordinates. So if you were to move, if the entirety of the Earth were to move a few nanometers to the left, because a big gravity wave rolled through, how would we know it? Well, nothing.
We don't have perception. It's like we can't perceive.
We wouldn't even
because we are in space-time, and space-time is the thing that is vibrating, and like the vibration, we don't have senses to capture that.
Right. A surfer is riding on top of the wave. It's connected to the wave, but it's decoupled by way of the atmosphere. So it can move with the heaviness of the water.
But a fish inside the water, he's
that's a good analogy.
Oh, there's actually I don't remember who the video was from, but there's actually a video of that. There are subsurface buoys for measuring things like tidal forces, and they're floating and they don't move. They do move up and down with the waves, but they never move like side to side with the waves. So
these are buoys that are not anchored?
I think they have some kind of inertial thing that keeps them from moving. I think they're going to be anchored by something that's, like 4,000 feet down in the middle of the Atlantic. But yeah, there's a lot of buoys out there, and you don't hear a lot of needing to reset the buoys when a seasonal giant wave rolls through. But yeah, it's probably a Veritasium video. Do things move in waves or not? But remember, there's neutrinos rolling through, there's gravity waves rolling through, and as far as we know, we're not moving.
Yeah, it's kind of like when you use the expression, oh, this makes no sense. And then you think about it, and you know that our senses are so limited as organisms that we are, that most of the science nowadays makes no sense. We can't hear under 20 decibels. We cannot see in between 400 and 700 nanometers of light. So it's like we're so limited in our senses, what we can hear, what we can see, that most of the science nowadays makes no sense. We have no senses, natural senses to capture that. So it's kind of,
It's
really
not
interesting.
intuitive. Yeah.
And
We have
then there's the opposite, where how long did we presume that when an electron gets excited, it instantaneously moves out to the outer orbital, and then instantaneously emits a photon and instantaneously goes to its ground state. It was always just, it's instantaneous. It takes no time at all. And now that we can measure time down to an incredibly tiny value of attoseconds, as like a thousandth of a thousandth of a thousandth of a nanosecond. Now that we can measure things to that level, when the photon comes in and the electron gets energized, we can actually see the electron accelerating towards the excitation level it achieves, and then emitting the photon. As it starts back down, it accelerates, and we actually know that the acceleration outward is faster than the acceleration inward. But prior to that, it was just magical. It happens instantaneously. There's a YouTube channel where guys have these ultra high speed solid state cameras, and they like to take pictures. I think they're called the slow mo guys.
Yeah, I've seen that.
They will, a million plus frames a second with this special camera, and you'll see things that you never even thought were possible as the effect of that. Oh, well, that doesn't happen instantaneously. You can actually see it like swell up and then burst, and there's a lot of things that just
I've seen videos. I've seen videos in university of pictures of a photon traveling through maybe a bottle or something like that.
Yes.
You can actually see the photon traveling, and that's like,
come on, it's only going at 186,000 miles a second. You just need a fast enough camera. But wait a minute, how does the camera capture an image? Photons enter the sensitive material and produce electrons. So how fast are well, it's relativistic. All the photons are moving at the speed of light. At the same time, yes. So we're back to the okay, if you say so. Well, we've got the math.
I think it was through a medium, so that how they could see it. Because then the light slowed down.
Right. The thing is, it's not the same photon from end to end. The photon gets absorbed and re-emitted all along the path. So it takes more time from beginning to end than the unimpeded time it would take to move. So it's the old adage of, hey, if light moves through a denser material, it travels slower. No, it always travels at the speed of light. It just gets absorbed, emitted, absorbed.
It's interacting more with the medium.
The propagation delay makes it appear to be traveling slower than the speed of light, but the individual photons are still traveling at the speed of light.
And even when you see X-ray in glass, if I'm not mistaken, the propagation is faster, but still moving at the speed of light. Yeah. Like the angle changes, and then if you calculate, it's supposed to move faster than light, but it's not.
Yes. Like tachyons.
Yeah.
Tachyons are supposed to move faster than the speed of light. Look it up. There are some constants that are out there that they don't make sense to be a constant, even if you evaluate the math and the physics. Like, why would it be that way? Well, if it wasn't that way, a lot of things would break. A lot of things wouldn't work right. So it's a foundational thing that just is. And it's kind of like,
well, when our overlord aliens explain that to us, we will understand.
I remember that episode of Stargate SG-1 where the Earth doctor was trying to explain wormholes to the extremely advanced alien, and he was saying like, well, it's like, if I've got a branch and there's 2 points at the end, and I make them come together, then that's a wormhole. Is that how we're gonna get your communications to go to your home planet a million light years away in less than the light travel time? He goes, no, that's not how it works. He didn't explain it. He just said, no, that's not how it works.
Yeah.
I thought that was just amazing. I'm sorry, you're too stupid a human despite your degrees, to even comprehend how it actually works. If in the 1920s, when Niels Bohr was coming up with his model of the atom, and it was explaining how photons and orbitals and stuff work. Remember, originally the orbitals were spherical, perfect circle shells. And now that we can actually measure all the possible places the electron could be, there's spheres and donuts and toroids that are twisted, and there's all kinds of orbital pattern. But until you can actually observe it, you don't really know what's going on. You just kind of, it's celestial spheres until we know better. And then it's not. And that's acceptable because that's the progression of scientific understanding.
Sometimes it's just a matter of looking at something from a different point of view.
Yes. Or
Yeah,
I
and
like to think
nowadays
of
the
it
different point of view is using instrumentation to observe things.
the ground rule we always have is you'll never know how much you didn't know until you know what you didn't know. So anytime there's a scientific advancement like, no, Andromeda is not a nebula, it's another galaxy. Okay, what you didn't know that you now know is, okay, everybody faced that direction now because we were facing that direction. Anything else before I stop recording?
Pretty good.